Okay, so this will be part 2 of exploring mathematics of the Rubik's Cube. And today we'll be going through how to intuitively calculate how many permutations of the Rubik's Cube there are. So now we're going to actually start incorporating moves. So if we do any amount of moves, how many different ways are there to arrange the Rubik's Cube? So first off, we can kind of assume that we can peel off stickers, right? So we'll take this red and then we'll swap it with this white. So this will become red and this will become white. So we're just, first we assume we can just peel off the stickers and just put it on any side. That's what we'll do first to get a big number, and then we'll start putting constraints on that to get the actual answer. So if we just look at the possibilities, there's 3 distinct types of pieces there are on the Rubik's Cubes. There's the corner pieces, right? They have 3 colors, corner pieces. And there's the side pieces, they have 2 colors. And then there's the center pieces, which only have 1 color. So there's the corner, the side, and the center. And what we want to do is basically calculate the possibilities for each type of piece. So for example, the corners, for the Rubik's Cube, we have 1, 2, 3, 4, and then 5, 6, 7, 8. So we have 8 corner pieces in total. So we could write that down, right? 8 corner pieces. Corner pieces. Oh, that might be hard to see. Yeah, 8 corner pieces. And then these have 3 colors, so we'll just say 3 colors. And we have 1, 2, 3, 4. It might be a little bit harder, a bit trickier to count the side pieces, but there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there's 12 side pieces. And then they have 2 colors each. 2 colors. And then there's 6 center, the ones that don't change. And then we have they each have 1 color. Boom. So we know that there's 8 corner pieces, 12 side pieces, and 6 center pieces. And pretty much with the centerpiece, since they don't move, right? No matter what sort of move you do, they don't really change. We can just say we know that without doing calculations, there's going to be no possibility, right? So no matter what move you do, they always remain the same relative to each other. And there's no move that you can do that'll be able to change the center. It always remains the same. So we know that as for the center, we can just kind of cross it off, right? Because it never changes no matter what we do. Now with the 8 corner pieces and 12 side pieces, we can start doing some calculations. So we know that there's 8 corner pieces. So if we were able to take one piece, right? Just take one piece and then put it in another spot. So let's say we swap this one with this one. Well, without caring for colors right now. So we just take this one, the white, orange, blue piece, and then we just swap it with the white, red, orange piece, right? So we just take this and put it here. Take this, put it here. Then if we can place any of the 8 pieces in any of the 8 locations, right? Place this here, then we know that's going to be 8 factorial, right? Because first there's 8 options, right? 8 options for any piece to go. Like let's say we take all the corners, right? So there's no corners. So this is gone, this is gone, this is gone, so there's 8 corners, and if we take any piece, there's 8 possibilities, right? So we slotted in 1 possibility, now there's 7. And then we take another piece, and then we put it in another space, and then now there's 6. And then 5, 4, 3, 2, 1, right? So it's 8 times 7 times 6 times, which would be 8 factorial. So we know that's that'll be 8 factorial. Just a fancy way of saying 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then with the 3 colors, we know that each piece, right, each individual piece has 3 colors, right? So this piece has 3 colors, this piece has 3, this, and then this, and this. All the 8 corners have 3 colors, right? Which means that because we have 8 pieces, if you think of it like kind of like a clock, we'll know that this has 3 possibilities, right? So we can have orange, white, green here, or we can twist it, right? So now it's orange, green, white here. Or if we were able to basically like take the stickers off, right? Take the stickers off and swap the sides, we'd be able to get 3 possibilities, which means this has 3 possibilities, this has 3 possibilities, so it's, 3 times 3 times 3 times 3 times 3 times 3, which is 3 to the power of 8. So it's 3 to the power of 8. Oh, it's not focusing, but it's 8 factorial, right? 8 factorial for swapping pieces, right? 8 factorial for swapping pieces, 3 to the power of 8 for swapping colors, right, on each piece. So 3 times 3 times 3 times 3. And then we do the same exact thing for the side pieces too. So we'll get 12 factorial times 2 to the 11, or sorry, 2 to the 12, 2 to the 12. Right, so that's what we get for the possibilities. 8 factorial times 3 to the 8, and then 12 factorial times 2 to the 12. And since these are the corner pieces and these are the side pieces, right, we just multiply them, right, because they're both the possibilities, right? And that's a pretty huge number, but we'll before computing that, we know that this will be likely more than what we can actually do with actual moves, right? Because we're assuming we can just take stickers, right? We can take one sticker and put it in another, and we're assuming we all possible all possible ways of peeling stickers, right? Like taking this orange and then putting it on the blue, and then taking this blue and putting it on the orange. So just swapping one piece, right, without changing the other. We're assuming that. But with actual moves of the Rubik's Cube, there's some other constraints, right? So there's some other constraints on this. So we'll divide this number by a couple of other numbers. So the first thing we can do is, if we notice when we do a move, right? When we do a move, let's take a look at, let's say, it's a bit hard to see. So we have this white, orange, green piece, right? The white, orange, green piece. So if we just lock our eyes here, right? Without changing, or without taking our eyes off this piece, right? So if we make this our center point, basically our focus point, anytime we do a move with this piece, right? Anytime we do a move with this piece, so let's say we move it this way, right? So lock our eyes here. When we do a move, we also realize we change these other pieces along with it, right? So while we change the white, orange, green piece, doing this move, right, doing the move that I did, it also changes the white, orange, blue piece, the white, red, blue piece, and the white, green, red piece, right? So they all come together, right? They all form, you can call it like a group, right? They all form like a happy group, right? This corner, this corner, this corner, and this corner. These four corners come together, right? As a collective, right? You can't move them separately. And if we do this move, right, to make it a little bit easier, we'll also just focus on, I said the white, green, red piece. There we go. Or white, green, orange piece. White, green, orange piece. So to make it easier to kind of see how the moves affect the corner pieces, let's just focus on the orange face, right? Just focus on the orange face. So if we move the top, right, the top of the orange face, like I said before, all these four corners come together, right? Though you can't move one corner without moving these other four corners. And it'll be the same if we do the right, if we rotate the right face, these four corners, this one, this one, this one, this one, they all move together, right? They all move together, the corners. So what this means is, if we move one corner, we have to move these four other corners, right? They they come together, basically. But then what does that mean, right? What does that mean with in terms of limitations with all the possible permutations? So if you think of it like you're kind of orienting the stickers. The green's a little bit hard to see. So you're orienting the sticker, this one of the sticker's colors, right? So with this, for example, all the pieces, they all have in common the orange face, right? The orange color. And anytime we move a face, right, you always have this one color, right? The one color that doesn't change, which is this color, right? The top colors, they don't change. And so whenever you make a move, you're always keeping one color the same. And that's a little bit it's a little bit tricky to kind of grasp, but intuitively what that means is, whenever we make like a random shuffling, like let's say we want to swap colors of corners. If we want to, let's say, it takes a bit of time, right? A bit of time to process. It's it's a bit tricky to understand intuitively. And math is all about exploration, so sometimes it takes time. It takes a lot of time to understand, and I think that's one of the most important things to learn about math, right? It's not instantaneous. So we've kind of come to a standstill. But a way to kind of figure this out is, right, what does that mean, right? What does keeping one face, one color the same mean? So if we think about it as in terms of color, right, the colors, we know that we can swap one piece with any other piece, right, by doing these moves. So we can swap this one with this one, 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 this one. We know that pretty much, right? If we do the right amount of a right combination of moves, we can swap one piece with another, right? Just the position, right? Position. We can swap this, right? For example, if we want to swap sides, right? So this green-white piece, right? If we want to swap the green-white piece with this, right? This side, right? We just have to rotate it this way, right? Just rotate it this way. So now it's here, right? The position swapped. And if we want to do it this way, right? If we want to swap it this way, we just have to rotate it this way. And if we want to rotate it this way, right, we just do 1, 2, right? And now the position swapped, right? The position swapped. And we can do that with this piece, this piece, this piece. And then because we know, right, because we know this piece can swap with this piece, right? this piece, position, right? We can swap the positions. We know this piece, right, by moving this way, can swap with any other piece here, right? So swap here, swap here, swap here, right? All these four can swap, right? We know because it's a cycle, right? Whenever we do a Rubik's Cube move, and then we know these four can swap. And because we can swap, right? And we know these four can swap, right? These four can swap, these four, and these four, right? All the four side pieces of each face can swap with each other, right? So if we return back to our green-white piece, right? If we return back, we can swap with this, right? But this can also swap with this, right? And this can swap with this. And this can swap with this. And these, right? These four can swap with each other, right? So we know any side piece can swap with any other side piece, right? Because this swaps with this, but this swaps with this. It's kind of like associative, kind of. But basically, right, any side piece swaps with any other side piece, right? Same with the corners, right? The corners, right? If we look at the cycle, 1, 2, 3, 4, these swap with each other, the positions, which means these swap with each other, these swap with each other. All corners and all sides can swap with each other, right? All sides swap with all other sides, all corners swap with all other corner. The positions, right? The positions. So we know we're not going to change these, right? 8 factorial is the positions, right? So these are positions. So we know these are pretty much locked in. What about the colors, right? 3 to the 8 colors, 2 to the 12 colors. There's something funky going on with the colors. And what it basically amounts to is when we change the color of one piece, we also change the color of another piece. So what do I mean by that? Like, let's focus on this, on the white side, for example. If we rotate it this way, right? So we're just rotating on the white face, right? So if we're rotating, I'll just do that move once again. So if we're rotating this way, now we see that all of these pieces, like I said before, their white side remains the same, right? So those four remain the same, but these two colors, the other two colors, they get shifted, right? Because, I mean, they do change positions, but they also change their colors as well. So let's say if I do two moves, for example, right, 1 and then 2. Oh, let me see. So this is white face, and then we do another move on the green face, right? So now what happens? Let's see. If we focus on this piece, for example, right? So we see this red, blue, white piece, and then we see this red, white, green piece. We've changed the color orientation, right? The color orientation of the red, blue, white piece. But when we change the color orientation, right, by moving it this way, so now we've changed the orientation, right? But when we change the red, blue, white piece, we also change the red, green, white piece along with it, right? They both change at the same time. So this piece has to change with this piece, both at the same time. And what that means is it's very tricky to understand intuitively. It's even difficult for myself. When you think of the Rubik's Cube as so we said there's, for example, the corners 3 to the 8 different colors. when we lock in the colors, right? So let's say this is, right? We're not changing the color, right? We're not changing the color of this or this or this or this, right? We're not changing the colors of these, right? We lock them in, right? And then we also lock it. So we have the white face and then we have the yellow face. They're just opposites of each other, just so you know. So we lock in the colors of these faces and these faces, and we lock in the colors of these faces and these faces. So what happens now? So let's say we want to just change the color of these two, right? The color of these two without changing any other color. And there's a couple ways to do that. Let's see. 1, 2, 2, 2, 2. Okay. So we see that right now. Oh, these are sides. But this'll apply to the corners as well. So that was a bit of a mistake, but we can learn something about the corners using the sides too. Now, doing that move, we see that when we swap the color, when we swap the colors of, sorry, first let's talk about the position. When we swap the positions of this guy, so red and white with this guy, red and yellow, right? So these two have swapped, right? These two sides have swapped, and these two sides have swapped, right? These two sides have swapped. So when we swap them back, right? When we just move them back, basically, right? When we just slide this guy back here, don't change, right? We do not change the color, the orientation. Then what we get is this, right? This is orange and white, right? This is orange and white. Sorry, orange and yellow, orange and yellow. So if we just shift it here, right, it becomes orange, right? Orange and yellow here. And then if we shift this here, it becomes orange and white, right? So it'll be off by a bit. Let's see. And what that means, and we can do that for the other side too. So we can do that for the other side. Instead of the orange, right? Instead of the orange, we can do that for the red side, right? So it'll be red and white, and it'll be red and yellow, right? So basically all the colors will be mismatched, right? Positions, right? The positions are correct, right? But the colors will be flipped. But the colors will be flipped for all 4 of these, right? So basically what that means is anytime we make a move that changes the color orientation, right? The color orientation of one of the pieces, it changes the color orientation of the other 4 pieces. So instead of it being 3 to the 8 colors, it'll actually be 3 to the 7 colors. And this will be the same for the colors of sides, right? Not instead of 2 to the 11, it'll be 2 to the 12. It'll be 2 to the 11. 2 to the 11 and 3 to the 7. All that's saying is when we lock in the colors, right? When we lock in the colors of the Rubik's Cube, so if we lock in the colors of all other 7 corners, 1, 2, 3. So let's say we see this green, orange, white piece, right? Green, orange, white piece. Don't think about any other piece, just focus on this, right? Focus on this. If we lock in every other color, right? Every other color, right? There's 3 to the 7 possibilities, right? Once we lock in all those colors, this also can't change. Because when we change one, right? When we try to change this piece, right? Without changing the other pieces, it's not possible using these moves, right? It's just, with the regular legal Rubik's Cube moves, no matter what we do, if we try to change the color of one thing, we always change the color of another thing. And I'm just reverting the Rubik's Cube back to normal. Here we go. So if we change the color, right, so if we, where's the green, orange, white piece? Here we go, this piece. So if we try to change the color of this without changing the colors of any other, so let's say this, so now it's in position, right? It's in position. This is the same green, white, orange piece, but it's, right, instead of it being this way, right, so white, green, orange, right, if we look at the centers, right, instead of it being white, green, orange, now it's white, green, orange, right? It's a different orientation. But when we change this, we also change this too, along with it, right? It changes from, instead of it being, or, where's the other piece? White, red, orange. White, green, orange. See, orange. White. Oh, here we go. My bad. And math is all about making mistakes, as always. That's the biggest lesson. And then learning from them. So, going back, we have the white, green, orange piece, right? And then it's oriented, right, differently. White, green, orange, right? So it's in position, but the colors are swapped. If we look at, orange, green, let me see, 2. We'll have to move one more piece into its corner. Green, red. Let me see. Red, white, orange, blue. Oh, here we go. So now let's take a look at all the corners. So this, right, we said previously it's in the position, but it's in the wrong orientation. Now this is also in position, right? If we just look at the center, white, orange, blue, white, orange, blue, but it's oriented wrong. And if we look at this one, right, it's in this right position, white, white, blue, blue, red, red, but it's in a different orientation. And if we just take a look at all the other corners, this isn't right color or orientation, right? Because the centers are different from the colors here. And then now let's take a look at the bottom, right? So this is in right place and right color. This is not the right place or right color. This is not the right place or right color, and then this is not right place or right color. So when we try to swap the colors of the corners, right? When we try to swap one of the colors of the corners, we always have to swap the colors of another corner. And that's no matter what we do. Because when you do a move, all of them come together, right? 1, 2, 3, 4. All 4 corners move together, right? They can't move independently. So when you lock in the colors, 1, 2, 3, 4, when you lock in the colors of the other 7 corners, the 8th corner always has to be oriented a certain way, basically. And that'll make more sense once I get into the very last aspect, right? So it's 3 to the 7, right? 3 to the 7 for corner colors, and 2 to the 11 for side colors, right? We're exactly the same argument, right? All these sides, right? This side, all 4 of them come together. Right? All 4 of them have to move together, right? Whatever I do. all 4 of them, 1, 2, 3, 4, have to move together. All of them. So now what's the last, right? What's the last part? This is a bit more abstract. And this will tie these two concepts together. When we do any move on a Rubik's Cube, right? When we do any move on a Rubik's Cube, right? So let's say we've got this, right? Got this orange face, let's do it counterclockwise, right? The very first layer. Boom, right? So when we do this move, right? Counterclockwise move on orange layer, how do we reverse it, right? How do we invert it? Or how do we return it back to normal, right? I mean, we just do, of course, the clockwise move, right? Clockwise, and we return everything back to normal, right? And you can do that with any, right? Any move, right? If we do it clockwise, counterclockwise, it doesn't matter, right? On any face, right? On any face, whatever move we do, we can return it back to normal in one step, right? But scrambling it, right? Doing it one and reverting it back to normal always takes 2 moves, right? Always takes 2 moves, right? First to scramble it, right? First to scramble it, and then to unscramble it, right? First to scramble it, and then to unscramble it. What does this mean, right? It means that the Rubik's Cube, if you want to use fancy terms for mathematics, it means it has even parity. All that it means is every move that we do on the Rubik's Cube is done in an even amount of ways. So, but we have to be more specific, right? We have to be more specific. When I scramble, right? Let's say 1, 2, 3, 4, 3, 4. So we scrambled in 4 moves, right? 4 moves, which means we can scramble back, right? We can return back in an even amount of moves. Right, so we have to count scrambling, right? Scrambling and unscrambling, right? Returning it back to the solved Rubik's Cube. We have to count both of these, right? We have to count both of these because these are both moves combined together, right? They're both combined together. So if we scramble an even amount of moves, like let's say 4, right? We did this in 4 moves. Then we know that unscrambling is also going to take an even amount of moves, right? Even plus even is all going to be even, right? And then if scrambling takes an odd amount of moves, right, then it takes odd amount of moves to unscramble, right? Odd plus odd is even.